Hello, welcome again. We are covering the topic centrifugal compressor for civil services mains IFS and Gate Aerospace exam. And the next topic in the next subtopic in the main topic of centrifugal compressor is backward swept curving. Okay. So we drive relationship for stagnation pressure ratio, for stagnation temperature ratio, for work done, okay, and for power required using radial curving. Now we will consider the case of backward swept curving. So backward swept curvings are increasingly being used for high performance compressor. So I will read it by point by point and explain each point. Okay. So this is your backward swept blade. So this is the radial direction like this. Okay. And now this blade is slightly back swept. Okay. So what is its step? So if we consider the ideal case of the velocity triangle at the impeller tip, then this is ideal case. CW2 is equal to U, this is your CR2 and this is your V2, and CR2 is equal to V2 also. But now this will remain the ideal case as shown by dotted line, but due to back swept, and if we consider zero slip, because this is for zero slip, then this V2 will automatically will be in this direction because of this back swept angle. So V2 will be in this direction because of this beta back swept angle of blades. Okay. And now this will be your CW2 because of this back sweep, and this will be your U. Initially this CW2 and U were equal, but now CW2 will be less than U, and one thing has to be noted, that still there is no slip. In this case there is no slip and CW2 is equal to U. In this case also there is no slip, but CW2 is not equal to U. That is due to this back sweep of the blade. CW2 is less than U, that is due to back sweep of the back swept angle of the blade of the blades. Okay. So it means this is your V2 and CR2 is same in both the cases. This is your CR2, this is CR2. Okay. Now this is your CW2, new CW2, and this is your C2 is C2 initially was this, now it is reduced. Okay. C2 is reduced, V2 is increased, CW2 is reduced. Okay. They both angles are for no slip, but CW2 is less when we consider back swept vanes. Okay. And what is the advantage of it? So advantage is that we have to supply less work, because work per unit mass is CW2U, and CW2 is less than U now, so it is now we will supply less work, but this less work will cause less temperature rise for the same pressure rise. Okay. But efficiency will increase, and there will be same pressure rise, but the temperature rise will be less due to less amount of work input. But our main goal is pressure rise, not the temperature rise. Okay. So back swept is your is an advantage. Okay. So back swept is your advantage. So I will read this and explain each and every point. The back swept curved vanes are increasingly being used for high performance compressor. Second point, the velocity triangle at the tip section of a back swept impeller is shown in figure, drawn for the ideal case of zero slip for the ease of understanding. So this is the velocity triangle, column 1 is for back sweep. Okay, here the slip is 0. Okay, drawn for the ideal case of zero slip for the ease of understanding. The corresponding triangle for radial vane impeller is shown by dotted line. So if we consider radial vane and zero slip, then this is a triangle. This is the triangle. The corresponding triangle for a radial vane impeller is shown by dotted line. Assuming the radial component of velocity to be same, implying the same mass flow. So here we have assumed that this CR2 is same for both the cases when we consider radial vane, when we consider backward swept vane. But it can be seen that the velocity relative to a tip V2 is increased. So in case of in ideal case this was V2, or sorry, in case of radial vane this was V2. Both are ideal case. This was V2, but now this is V2. So V2 is increased, while absolute velocity C2 is reduced. In case of radial vane, this was C2. Now this is your C2. While absolute velocity C2 is reduced. These changes imply less stringent diffusion in both impeller and diffuser, tending to increase efficiency of both components. So if C2 is reduced, it means CW2 is also reduced. Initially it was this, now it is this. So it will require less amount of work, less stringent diffusion requirement in both impeller and diffuser, tending to increase the efficiency of both components. The efficiency of the component will increase. Next point is the back sweep beta may be in the region of 30 to 40 degrees. So this can be of 30 to 40 degrees. The work absorbing capacity of the rotor is reduced, because now the work input that can be input is CW2 into U, and CW2 is less than U. But when we consider radial vane, CW2 is equal to U. So work absorbing capacity is reduced because CW2 is lower. As work absorbing capacity is reduced, so this work absorbed increases the temperature. So temperature rise will also be reduced. So temperature rise will be less than would be obtained with the radial vane. Okay. So temperature rise would be less, but the pressure rise would remain same, because of the process will reach close to isentropic system, or the efficiency of the process will increase. This effect is encountered by increased efficiency, and it must be remembered that ultimate goal is with high pressure. Now for the lesser temperature we can achieve same pressure ratio. Okay, so the backward swept vanes are advantageous. So backward swept, so that was the topic, backward swept vanes. So these are advantages.